The Monty Hall problem is a probability puzzle that has unsettled and confused millions of people, including professional mathematicians, because its correct solution contradicts strong intuitions about chance and fairness. The problem is based on a game show scenario. You are a contestant facing 3 closed doors. Behind one door is a valuable prize, and behind the other 2 doors are worthless goats. You choose a door, say door number 1. Before opening your chosen door, the host, who knows what is behind all the doors, opens a different door, say door number 3, revealing a goat. Now, 2 doors remain closed, your original choice, door 1, and the unchosen door number 2. The host offers you a choice. You can stick with your original selection, door 1, or you can switch to door number 2. What should you do? Most people's intuition says that it does not matter because there are 2 doors left, and the prize is equally likely to be behind either one. Therefore, switching and staying have the same probability of winning. But this intuition is wrong. The correct strategy is to always switch, because switching gives you a 2/3 probability of winning, while staying gives you only a 1/3 probability. The reason switching is better requires careful analysis of what information the host's action provides. When you initially choose door 1, there is a 1/3 chance the prize is behind door 1 and a 2/3 chance the prize is behind one of the other 2 doors. These initial probabilities do not change when the host opens door 3. The host's action is not random. The host always opens a door that has a goat and is not your chosen door. If the prize is behind door 1, which happens 1/3 of the time, then both doors 2 and 3 have goats, and the host can open either one. If the prize is behind door 2, which happens 1/3 of the time, then the host must open door 3 because door 2 has the prize and door 1 is your choice. If the prize is behind door 3, which happens 1/3 of the time, then the host cannot open door 3, so this scenario does not match what happened in our problem. So, given that the host opened door 3, we know that either the prize is behind door 1, which had a 1/3 initial probability, or the prize is behind door 2, which had a 2/3 initial probability. Since these probabilities sum to 1 and must be redistributed among the remaining possibilities, door 2 now has a 2/3 probability and door 1 still has a 1/3 probability. Switching doubles your chances of winning. When this problem was presented in a popular magazine column in 1990 by Marilyn Vos Savant, she received thousands of letters from readers, including many with PhDs in mathematics, insisting she was wrong. The intuition that 2 closed doors should represent equal probabilities is extremely strong, and the correct solution feels wrong even when the logic is explained clearly. This reveals something unsettling about human reasoning under uncertainty. Our intuitions about probability are often deeply flawed, leading us to incorrect conclusions with high confidence. Even experts can be misled by probability problems that have subtle structure. The Monty Hall problem has become a famous example of cognitive bias, illustrating how our brains use heuristics and shortcuts that work well in many situations but fail in cases with specific informational asymmetries. The host's knowledge and constrained behavior create a correlation between the prize location and the host's action that transfers information to the contestant in a non-obvious way. Failing to account for this correlation leads to the wrong answer. The unsettling aspect of the Monty Hall problem is not just that it is counterintuitive, but that it reveals how easily we can be wrong about objective truth even when we feel certain. Probability and statistics govern much of modern life, from medical diagnoses to financial decisions to legal judgments. Yet human intuitions about probability are systematically flawed in predictable ways. We overestimate the likelihood of vivid or recent events. We see patterns in random noise. We ignore base rates when making predictions, and we struggle to correctly update beliefs in light of new evidence. These cognitive biases can have serious consequences. Juries misinterpret statistical evidence. Doctors misunderstand diagnostic test results. Investors make poor choices based on faulty probability judgments. The Monty Hall problem serves as a humbling reminder that our subjective feeling of certainty is not a reliable guide to truth. We can be absolutely confident and completely wrong. This suggests the need for careful reasoning, for checking our intuitions against formal analysis, and for intellectual humility in the face of complex probabilistic scenarios. The universe does not always operate according to our gut feelings, and recognizing this gap between intuition and reality is both uncomfortable and essential for making better decisions. Prime numbers stand alone in the vast landscape of mathematics, like ancient monuments scattered across an endless desert. A prime number can only be divided by itself and 1, which makes each prime a kind of mathematical island, isolated from the patterns that govern other numbers. When mathematicians first began studying primes thousands of years ago, they noticed something unsettling about these numbers. They appear randomly scattered along the number line with no predictable pattern, yet they are the building blocks of all other numbers. Every whole number greater than 1 is either prime or can be broken down into a unique combination of prime factors. This fundamental theorem of arithmetic means that primes are simultaneously random and essential, chaotic and foundational. The ancient Greeks were fascinated by primes and proved that there are infinitely many of them, stretching forever into the vast expanse of numbers beyond our comprehension. But the question that haunted mathematicians for centuries was whether there exists any pattern or formula that could predict where the next prime would appear. As numbers grow larger, primes become increasingly rare, like stars dimming in an expanding universe. Between small numbers, primes appear relatively frequently. Among the first 10 numbers, we find 4 primes. Among the first 100 numbers, we find 25 primes. But as we journey into millions and billions and beyond, the gaps between consecutive primes grow wider and more irregular. Yet mysteriously, primes never disappear completely. No matter how far you travel along the number line, another prime always awaits somewhere ahead. This eternal presence combined with unpredictable spacing creates an unsettling tension in mathematics. Imagine walking through a dark forest where you know there are landmarks ahead, but you never know when you will encounter the next one. The uncertainty creates both anxiety and anticipation. Mathematicians developed sophisticated methods to search for larger and larger primes, and in doing so, they discovered patterns within the apparent randomness that are both beautiful and disturbing. One of the most unsettling aspects of prime numbers involves twin primes, which are pairs of primes separated by just a single even number. Examples include 3 and 5, 11 and 13, 17 and 19. These twin primes seem to appear frequently among smaller numbers, creating a sense of companionship in the loneliness of primality. 2 primes standing together, almost touching, separated by the thinnest possible gap. But as numbers grow larger, twin primes become increasingly rare, and mathematicians began to wonder whether twin primes continue forever or eventually disappear completely. This question, known as the twin prime conjecture, remains one of the greatest unsolved problems in mathematics. We believe twin primes continue infinitely, appearing like distant binary stars in the cosmic void of numbers, but we cannot prove it with certainty. The thought that somewhere far along the number line, twin primes might suddenly cease to exist, leaving all subsequent primes in eternal isolation, carries a melancholic weight that touches something deep in the human psyche. The distribution of prime numbers was studied intensely in the 19th century when mathematicians discovered the prime number theorem, which describes approximately how many primes exist below any given number. This theorem shows that primes become less dense as numbers increase, but they thin out in a predictable way that can be described by logarithms. Yet, even with this understanding, the precise location of individual primes remains mysterious. The Riemann hypothesis, proposed in 1859 and still unproven today, suggests a deep connection between prime numbers and a complex mathematical function called the Riemann zeta function. This hypothesis, if true, would reveal that the apparent randomness of primes actually follows an extraordinarily subtle pattern encoded in the complex plane, a mathematical space where numbers have both real and imaginary components. The idea that prime numbers, which seem scattered without reason, might actually dance to a hidden rhythm involving imaginary numbers is both beautiful and deeply unsettling. It suggests that reality itself operates on multiple levels simultaneously, with surface chaos masking underlying order. Infinity is not a number, but a concept that breaks the rules we use for ordinary counting and arithmetic. When we try to apply mathematical operations to infinity, strange and counterintuitive results emerge that challenge our basic understanding of quantity and size. One of the most unsettling thought experiments involving infinity is known as Hilbert's Hotel, named after the mathematician David Hilbert, who used it to illustrate the paradoxical properties of infinite sets. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on forever. One night, every single room in this infinite hotel is occupied. Every room has a guest, and there are no vacancies whatsoever. Now imagine a new guest arrives at the front desk requesting a room. In any normal hotel, the manager would apologize and explain that the hotel is completely full. But in Hilbert's infinite hotel, the manager smiles and says there is no problem. The manager asks the guest in room 1 to move to room 2, the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Every current guest moves to a room number that is double their current room number. This means all the odd-numbered rooms are now empty, and since there are infinitely many odd numbers, there are infinitely many vacant rooms for the infinitely many new guests. The hotel was full, accommodated infinite new guests, and everyone still has a room. This violates our intuitive understanding that adding anything to a full container should cause overflow. But in the realm of infinity, the rules change in profoundly disturbing ways. What makes this paradox particularly unsettling is that it reveals a fundamental property of infinite sets discovered by Georg Cantor in the late 19th century. An infinite set can be placed in one-to-one correspondence with a proper subset of itself, which is impossible for finite sets. The set of all positive integers is infinite, and the set of all even positive integers is also infinite. Our intuition suggests that there should be twice as many positive integers as even positive integers, because evens represent only half of all integers. But Cantor showed that both sets have exactly the same size of infinity, meaning they are the same size of infinity. You can pair each positive integer with an even positive integer by doubling it, creating a perfect one-to-one match with nothing left over on either side. This means that half of infinity is still the same size of the whole infinity. Removing infinitely many elements from an infinite set does not make it smaller in terms of cardinality. These ideas violate our everyday experience with quantities and challenge our ability to think clearly about the infinite. Cantor went even further and proved something that shocked the mathematical world. He demonstrated that not all infinities are equal in size. The infinity of counting numbers, which can be listed in a sequence even though the sequence never ends, is smaller than the infinity of real numbers, which include all decimals and cannot be completely listed. Cantor proved this through his famous diagonal argument, showing that any attempt to list all real numbers must necessarily leave out infinitely many real numbers. This means there are different levels of infinity, hierarchies of endlessness stacked upon each other, reaching upward forever. The smallest infinity is called countable infinity, exemplified by the natural numbers. The next larger infinity is the continuum, exemplified by the real numbers. But there are even larger infinities beyond that, an infinite tower of increasing infinities with no ultimate largest infinity. The human mind struggles to grasp even one infinity, and the idea that infinities can be compared and ranked in size creates a vertigo of comprehension. We stand at the edge of a conceptual abyss, looking down into layers of endlessness that descend beyond sight, and the experience is both terrifying and strangely peaceful. Fractals are geometric patterns that repeat at every scale, revealing the same structure whether you zoom in close or pull back far away. These mathematical objects were formalized in the 20th century, though examples had been discovered earlier. The most unsettling property of fractals is that they often possess infinite complexity within a finite space. Consider the Koch snowflake, a fractal constructed through a simple iterative process. You begin with an equilateral triangle. On each side of the triangle, you remove the middle third and replace it with two sides of a smaller equilateral triangle, creating a star-like shape. Then you repeat this process on every straight line segment, adding smaller and smaller triangular bumps forever. As you continue this process infinitely many times, the resulting shape is the Koch snowflake. This snowflake can fit inside a small circle, occupying a clearly finite area, but its perimeter, the length of its boundary, is infinite. Every iteration adds more length to the perimeter, and because the iterations continue forever, the perimeter grows without bound, even though the area remains finite. How can something have a finite area but an infinite perimeter? This violates our intuitive understanding of shapes and boundaries. If you tried to walk around the perimeter of a Koch snowflake, you would walk forever, never completing your journey, never returning to your starting point. Yet you would always remain close to the same small region of space. The fractal boundary twists and turns with such complexity that it becomes longer than any finite length while never expanding beyond a limited region. This property challenges the classical geometric concepts developed by the ancient Greeks, who believed that all shapes could be understood through combinations of simple forms like lines, circles, and polygons. Fractals revealed that nature operates on principles far more complex than classical geometry suggested. Coastlines, mountain ranges, clouds, trees, rivers, and countless other natural phenomena display fractal properties, with similar patterns appearing at multiple scales. The Coastline Paradox states that the measured length of a coastline depends on the scale of measurement. As you use smaller and smaller measuring units, accounting for tinier and tinier details, the measured length increases without limit. Britain's coastline is infinitely long if measured with perfect precision, yet Britain clearly occupies a finite area. Another deeply unsettling fractal is the Mandelbrot set, discovered through computer visualization in 1980. This set is defined through a remarkably simple mathematical rule involving complex numbers, yet it produces the most intricate and elaborate shape ever discovered in mathematics. The boundary of the Mandelbrot set is a fractal curve of infinite complexity, containing endless spirals, tendrils, and self-similar structures that echo the main shape at every level of magnification. As you zoom into the boundary, you discover new structures that resemble the whole set, but with variations and embellishments that are unique. You can zoom in forever, magnifying by factors of millions and billions and beyond, and you will always find new details, new patterns, new structures that no one has ever seen before. The Mandelbrot set is a single mathematical object defined by a simple formula, yet it contains infinite richness. Explorers of the Mandelbrot set have spent decades zooming into different regions, documenting the structures they find, and they have barely scratched the surface of its infinite complexity. The philosophical implications of fractals are profound and unsettling. They suggest that complexity does not require complicated rules. The simplest instructions, repeated infinitely, can generate structures of unlimited intricacy. This has implications for understanding how nature creates the complex forms we observe. Evolution operates through simple rules applied repeatedly over time, and perhaps the infinite complexity of biological life emerges through fractal-like processes. The universe itself may possess fractal properties at cosmic scales, with galaxies clustered in patterns that repeat at multiple levels of zoom. If reality is fundamentally fractal, then there may be no smallest scale, no ultimate building blocks, no final level of resolution. Zooming into atoms reveals subatomic particles. Zooming into those reveals quarks, and perhaps zooming into quarks reveals even smaller structures in an endless descent. Similarly, zooming out from galaxies reveals superclusters, and perhaps those are part of even larger structures in an endless ascent. The possibility that reality has no ultimate scale in either direction, that existence is infinitely deep and infinitely vast, creates a dizzying sense of vertigo that can either disturb us or, paradoxically, bring us peace through accepting the limits of human comprehension. The Banach-Tarski Paradox is perhaps the most counterintuitive and unsettling result in all of mathematics. It states that it is theoretically possible to take a solid sphere, divide it into a finite number of pieces using precise cuts, and then reassemble those pieces through rotations and translations alone into two complete spheres, each the same size as the original. This appears to violate basic conservation principles. How can you create more volume from nothing, doubling a sphere without adding any material? The paradox was proved in 1924 by Stefan Banach and Alfred Tarski, and it remains one of the most philosophically troubling results in mathematical logic. The key to understanding this paradox lies in the nature of the pieces into which the sphere is divided. These are not ordinary pieces that you could hold in your hand or visualize in space. They are infinitely complex sets of points defined through abstract mathematical rules that do not have well-defined volumes in the ordinary sense. The axiom of choice, a controversial principle in set theory, allows mathematicians to construct these bizarre sets by making infinitely many arbitrary selections simultaneously. The pieces in the Banach-Tarski decomposition are so pathologically complicated that they cannot be measured in any conventional sense. They are not connected regions, but scattered clouds of points distributed throughout the sphere in patterns of such extreme complexity that they defy visualization. When you rotate and translate these pieces, you are not moving solid chunks of matter, but rather relocating infinitely intricate point sets according to mathematical rules. The paradox works because these non-measurable sets can interlock and overlap in ways that ordinary objects cannot. In the physical world, matter is made of atoms, which are discrete units, so you cannot actually perform a Banach-Tarski decomposition on a real sphere. But in the pure realm of mathematical points, where a sphere is treated as an infinite collection of dimensionless locations in space, the axiom of choice permits constructions that violate our intuitions about conservation and quantity. This reveals a deep tension between mathematical abstraction and physical reality, suggesting that mathematics, when pushed to its logical extremes, describes structures and possibilities that cannot exist in the universe we inhabit. The Banach-Tarski Paradox raises profound questions about the nature of infinity and the foundations of mathematics. The axiom of choice, which enables this paradox, states that given any collection of non-empty sets, it is possible to choose exactly one element from each set, even if the collection is infinite and even if there is no rule specifying how to make the choices. This seems innocuous and even obvious when stated abstractly. If you have 1,000,000 boxes, each containing at least one ball, surely you can select one ball from each box. But when the number of boxes is infinite, and when the contents of the boxes are themselves infinite and complex, the axiom of choice leads to conclusions that seem impossible. Some mathematicians reject the axiom of choice, arguing that mathematics should only work with sets and constructions that can be explicitly defined and visualized. Without the axiom of choice, the Banach-Tarski paradox cannot be proved. But the axiom of choice is extraordinarily useful for proving many important theorems throughout mathematics, and most mathematicians accept it despite its counterintuitive consequences. This means mainstream mathematics endorses a framework in which spheres can theoretically be duplicated through decomposition and reassembly, even though such an operation could never be realized physically. The deeper, unsettling aspect of Banach-Tarski involves what it suggests about the nature of mathematical truth. Is mathematics discovered or invented? If mathematics is discovered, then Banach-Tarski paradox represents a true fact about the abstract realm of mathematical objects, revealing that reality at its most fundamental level operates according to rules that defy our physical intuitions. If mathematics is invented, then Banach-Tarski is an artifact of the particular axioms and rules we chose to adopt, and we could have constructed a different mathematics without this paradox by making different foundational choices. Either possibility is disturbing. The first suggests that truth itself is stranger than our minds can comfortably grasp. The second suggests that mathematics, which we rely upon to describe reality with precision and certainty, is ultimately an arbitrary human construction that we could have built differently. For those seeking certainty and objective truth, mathematics has always seemed like the solid ground upon which to stand. But results like the Banach-Tarski paradox reveal cracks in that foundation, showing that even in mathematics we must make choices about axioms and accept consequences that violate intuition. Perhaps there is no escape from ambiguity and paradox even in the most abstract and logical domains of human thought. In 1931, a young mathematician named Kurt Godel published a theorem that shook the foundations of mathematics and logic. Godel's incompleteness theorem proved that any formal system of mathematics that is powerful enough to describe basic arithmetic must be either incomplete or inconsistent. Completeness means that every true statement within the system can be proved using the system's axioms and rules. Consistency means that the system never proves contradictory statements. Mathematicians had hoped to create a formal system that was both complete and consistent, a perfect logical framework within which all mathematical truths could be systematically derived and verified. Godel proved that this dream is impossible. In any consistent mathematical system, there must exist true statements that cannot be proved within that system. These unprovable truths exist in a strange limbo, hovering beyond the reach of formal proof, yet recognizably true when examined from outside the system. The implications of this result are profound and unsettling, suggesting that human knowledge will always be incomplete, that there will always be truths we can perceive but cannot formally demonstrate. Godel's proof works through a brilliant self-referential construction. He showed how to encode mathematical statements as numbers, turning mathematics into a system that can talk about itself. Then he constructed a specific statement that essentially says, this statement cannot be proved within this system. If the system could prove this statement, then the statement would be false, meaning the system proves false statements and is inconsistent. If the system cannot prove this statement, then the statement is true, meaning there exists a true statement that the system cannot prove and the system is incomplete. Either way, the goal of a complete and consistent system is unattainable. This self-reference creates a mathematical analog to the ancient liar paradox, where someone says, "I am lying," and we cannot consistently assign a truth value to their claim. But whereas the liar paradox seems like a linguistic trick, Gödel's theorem operates within the rigorous framework of formal logic and applies to actual mathematical systems. It reveals that self-reference creates genuine logical limitations that cannot be avoided or worked around. The unsettling nature of Gödel's incompleteness deepens when we consider its implications for the foundations of mathematics. Mathematicians like David Hilbert had hoped to formalize all of mathematics as a game played with symbols according to strict rules, where every truth could be mechanically derived from axioms. This would have made mathematics completely certain and objective, free from ambiguity or doubt. Gödel showed that this vision is fundamentally unattainable. There will always be statements that mathematicians can recognize as true through intuition and informal reasoning, but that cannot be captured within any single formal system. To prove these statements, we need to step outside the system, adopt additional axioms, and create a larger system. But the new larger system will have its own unprovable truths, requiring yet another expansion. This process never ends. Mathematics is not a closed system of derivable truths, but an open-ended exploration that can never be completed. For some, this is liberating, suggesting that mathematics will always offer new frontiers to explore. For others, it is deeply troubling, undermining the dream of absolute certainty and perfect knowledge. Gödel's second incompleteness theorem, proved shortly after the first, adds another layer of unsettling depth. It shows that a consistent formal system cannot prove its own consistency. If we construct a mathematical system and want to verify that it will never produce contradictions, we cannot use the system itself to perform that verification. We need a stronger external system. But then we face the same problem with that system, leading to an infinite regress. This means we can never have absolute certainty that our mathematical foundations are consistent. It is possible, though most mathematicians believe unlikely, that standard mathematics contains a hidden contradiction that will someday be discovered, causing the entire edifice to collapse. We proceed with confidence based on decades of experience and the absence of contradictions found so far, but Gödel proved that we cannot have logical certainty. We are walking on ground we cannot fully verify, trusting it to hold our weight even though we cannot prove it is solid all the way down. This parallels the human condition more broadly, where we must act and make decisions without certainty, trusting in patterns and experiences that could someday prove unreliable. Mathematics, the supposedly firmest foundation of human knowledge, turns out to rest on assumptions we cannot fully validate, making it more similar to other domains of human knowledge than we might wish to admit. The Coastline Paradox is a geographical observation that reveals unsettling truths about measurement and the nature of length. When we try to measure the length of a coastline, the answer we get depends entirely on the scale of our measuring tool. If you use a large ruler and measure the coastline in kilometer-long segments, you get one answer. If you use a smaller ruler and measure in 100-meter segments, following the curves and inlets more closely, you get a longer answer. If you use an even smaller ruler, measuring meter by meter around every rock and irregularity, you get an even longer answer. As the measuring scale decreases, the measured length increases without apparent limit. If you could measure at the scale of individual grains of sand, accounting for every tiny indentation and protrusion, the coastline would be extraordinarily long. At the molecular scale, it would be longer still. In theory, the coastline has no well-defined length. It is a fractal-like structure whose measured length approaches infinity as the precision of measurement increases. This means we cannot answer the simple question, how long is the coastline, without specifying the scale of measurement. There is no single true answer, only a family of answers depending on resolution. This paradox was formally identified by Louis Fry Richardson in the early 20th century and later popularized by Benoit Mandelbrot, the mathematician who gave fractals their name. Richardson was studying whether countries with longer shared borders were more likely to go to war, and he discovered that different countries reported different lengths for the same shared border. Spain and Portugal disagreed on the length of their border, as did Belgium and the Netherlands. Richardson realized this was not due to poor measurement technique, but rather to different measurement scales. Smaller countries naturally used finer measurements and reported longer borders, while larger countries used coarser measurements and reported shorter borders. Both measurements were correct for their respective scales, but they could not be directly compared. This revealed that the concept of length, which seems so fundamental and objective, actually depends on the observer's perspective and methodology. Two people measuring the same object with different tools will get different answers, and neither answer is more correct than the other in absolute terms. The Coastline Paradox connects to fundamental questions in physics about the nature of space and measurement. In classical physics, we imagine space as infinitely divisible. We can always zoom in closer, using finer measurements, revealing more detail at smaller scales. But quantum mechanics suggests that space may not be infinitely divisible. There may be a smallest meaningful scale, the Planck length, below which the classical concept of distance breaks down and quantum fluctuations dominate. If space has a minimal scale, then coastlines do have definite finite lengths when measured at that scale, and the coastline paradox is resolved by physical limits rather than mathematical considerations. However, even if space is quantized at the Planck scale, practical measurements occur at much larger scales where the paradox remains relevant. When cartographers draw maps, they must choose a resolution, and that choice determines the lengths they will measure and report. Every map is a simplification that suppresses details below a certain scale, and different simplifications produce different numerical results. The philosophical implications of the coastline paradox extend beyond geography. Many natural phenomena display similar scale-dependent properties. Clouds have no definite surface area because their boundaries are diffuse and fractal. Trees have no definite total branch length for similar reasons. Rivers have no definite length because their paths twist and turn at multiple scales, and measuring finely enough to capture every meander yields arbitrarily long results. Even seemingly simple objects may have scale-dependent properties. The surface area of a crumpled piece of paper depends on how closely you measure the microscopic hills and valleys in the material. Reality, when examined carefully, resists simple quantification. The numbers we use to describe the world are not objective properties waiting to be discovered, but rather context-dependent values that emerge from our interaction with phenomena at particular scales. This suggests that much of what we call measurement is actually a negotiation between the observer and the observed, where our tools and methods shape the answers we receive. The quest for objective, observer-independent truth becomes more complicated when we realize that even basic properties like length depend on how we choose to look. Zeno of Elea was an ancient Greek philosopher who lived around 2,500 years ago and created a series of paradoxes designed to challenge common-sense beliefs about motion, space, and time. These paradoxes remain philosophically unsettling, even though modern mathematics has provided formal resolutions. The most famous is the paradox of Achilles and the tortoise. In this paradox, the great warrior Achilles races against a slow tortoise. Achilles, being much faster, gives the tortoise a head start. Zeno argues that Achilles can never overtake the tortoise through the following reasoning. By the time Achilles reaches the point where the tortoise started, the tortoise has moved a little bit ahead. When Achilles reaches that new point, the tortoise has moved a little bit further. This process continues infinitely. Every time Achilles reaches where the tortoise was, the tortoise has advanced, and there are infinitely many such stages. Since Achilles must complete infinitely many stages to catch up, and completing infinity seems impossible, Achilles never overtakes the tortoise. Yet in reality, fast runners easily overtake slow ones, so something must be wrong with Zeno's reasoning. The resolution to this paradox requires understanding infinite series and limits, concepts that were not fully formalized until the 19th century with the development of calculus. Each stage in Zeno's argument takes less time than the previous stage. If the tortoise has a 10-meter head start and Achilles runs 10 times faster, then Achilles covers the first 10 meters in some time, the tortoise advances 1 meter, Achilles covers that 1 meter in 1/10 the previous time, the tortoise advances 1/10 of a meter, and so on. The times form an infinite geometric series that sums to a finite value. Achilles completes infinitely many stages in finite time, and then he overtakes the tortoise. The key insight is that summing infinitely many terms does not necessarily give an infinite result. If the terms decrease rapidly enough, the infinite sum converges to a finite limit. This mathematical resolution is satisfying from a technical standpoint, but it leaves deeper philosophical questions unresolved. How can Achilles complete infinitely many distinct actions in finite time? Does motion require completing infinitely many sub-motions? And if so, what does that mean for the nature of physical action? Another of Zeno's paradoxes concerns the arrow in flight. Zeno argues that at any single instant of time, an arrow occupies a specific position in space equal to its own length. At that instant, the arrow is not moving to a new location because an instant has no duration. If the arrow is motionless at every instant, then it is always motionless, and motion is impossible. This paradox challenges our conception of instantaneous velocity. In calculus, velocity at an instant is defined as a limit of average velocities over progressively shorter time intervals. This definition avoids saying that an object actually moves during an instant, instead describing velocity as a mathematical relationship between position and time. But does this really explain motion, or merely provide a formal framework for calculating trajectories? The philosophical question remains whether motion is a fundamental feature of reality, or an emergent property arising from sequences of static states. If time is composed of discrete instants and nothing moves during a single instant, then how does change occur? If time is continuous rather than discrete, then what is an instant, and how can we meaningfully talk about instantaneous properties? Zeno's paradoxes highlight the tension between our intuitive understanding of the continuous physical world and the logical structure of mathematical reasoning. When we model space and time using real numbers, we implicitly assume that any finite interval can be subdivided into infinitely many smaller intervals. This infinite divisibility is essential for calculus and modern physics, but it leads to conceptual puzzles about how finite quantities relate to infinite processes. The unsettling aspect is that our most successful physical theories rely on mathematical structures that seem metaphysically strange. Quantum mechanics introduces additional complications, suggesting that space and time may not be perfectly continuous at the smallest scales. The Planck length and Planck time represent scales at which quantum fluctuations become significant. And some theories propose that space-time is fundamentally discrete or granular at these scales. If so, then Zeno's paradoxes might be resolved by physical limits rather than mathematical techniques. But this substitutes one mystery for another, leaving us to wonder about the true nature of the substrate upon which motion and change unfold. Whether continuous or discrete,
Reality operates according to principles that challenge our intuitive categories, and grappling with these challenges bring both intellectual discomfort and a strange sense of awe.
Georg Cantor's work on infinity in the late 19th century revolutionized mathematics and revealed unsettling truths about the nature of mathematical existence. Cantor proved that the set of real numbers is fundamentally larger than the set of natural numbers, even though both are infinite. This result, known as the uncountability of the reals, shows that not all infinities are created equal. The proof uses a technique called the diagonal argument, which is remarkably simple yet profound in its implications. Suppose someone claims to have listed all the real numbers between 0 and 1. Each real number is represented as an infinite decimal expansion. Cantor showed how to construct a new real number that is definitely not on the list, proving the list is incomplete. To construct this new number, look at the first digit after the decimal point in the first number on the list and choose a different digit for the first digit of your new number. Look at the second digit of the second number on the list and choose a different digit for the second digit of your new number. Continue this process for every position. The resulting number differs from every number on the list in at least one decimal place, so it cannot be on the list. Since any proposed list can be shown to be incomplete, no complete list exists, and the real numbers are uncountable. This argument is elegant and seemingly airtight, yet it disturbed many mathematicians when Cantor first presented it. The conclusion implies that the real numbers form a larger infinity than the natural numbers, which can be listed in a sequence 1, 2, 3, and so on. The technical term is that the natural numbers are countably infinite, while the real numbers are uncountably infinite. This distinction might seem like a technicality, but it has profound implications for the structure of mathematics. Most individual real numbers cannot be explicitly described or computed because there are uncountably many real numbers, but only countably many possible descriptions using finite strings of symbols. Almost all real numbers are incomputable and indescribable, existing in a mathematical realm beyond our ability to access or manipulate them individually. This creates a strange situation where we can prove that certain objects exist and reason about their collective properties, but we cannot exhibit specific examples or interact with them directly. It is as if mathematics contains a vast, dark ocean of entities that we know are there, but can never bring into the light of explicit representation. Cantor's work faced fierce resistance from some of his contemporaries. Leopold Kronecker, a prominent mathematician, opposed Cantor's ideas about infinite sets and argued that mathematics should only deal with constructive, finitely describable objects. Kronecker believed that infinite sets and non-constructive existence proofs were philosophical confusions rather than legitimate mathematics. This dispute reflects a deep divide in mathematical philosophy between those who view mathematics as the study of abstract objects that exist independently of human minds, and those who view mathematics as a human construction that should be grounded in concrete procedures. Cantor suffered from depression and spent periods in mental institutions, possibly exacerbated by the hostile reception to his work. Yet his ideas ultimately prevailed and became the foundation of modern set theory. Today, mathematicians routinely work with infinite sets of different cardinalities, and Cantor's hierarchy of infinities is a standard part of mathematical education. But the philosophical questions he raised remain unresolved. Do uncountable sets really exist, or are they convenient fictions that help us organize mathematical reasoning? If they exist, where do they exist? And what does it mean to say that mathematical objects have existence independent of physical reality? The most unsettling aspect of Cantor's work may be the continuum hypothesis, which Cantor himself considered but could not resolve.
The continuum hypothesis asks whether there exists an infinity strictly between the countable infinity of natural numbers and the uncountable infinity of real numbers. Cantor believed no such intermediate infinity exists, but he could not prove it. In the 20th century, Kurt Godel and Paul Cohen proved that the continuum hypothesis is independent of the standard axioms of set theory. This means that within the usual framework of mathematics, the continuum hypothesis can neither be proved nor disproved. It is consistent to assume the hypothesis is true, and it is equally consistent to assume the hypothesis is false. Mathematicians can choose which assumption to adopt, and different choices lead to different mathematical universes with different theorems and properties. This reveals that mathematics is not a single fixed structure, but rather a landscape of possibilities, where foundational choices shape the nature of mathematical truth. The idea that something as seemingly fundamental as the size of the continuum is not determined by logic alone, but requires an additional choice or axiom, suggests that mathematics contains an element of contingency or creativity that goes beyond pure deduction from first principles.
The birthday paradox is a famous result in probability theory that surprises most people when they first encounter it. The question is simple. In a room full of randomly selected people, how many people must be in the room before there is a better than 50% chance that at least 2 people share the same birthday? Most people's intuition suggests a large number, perhaps more than 100, because there are 365 days in a year, and finding a match among so many possibilities seems unlikely with a small group. But the correct answer is only 23 people. With 23 randomly selected people in a room, there is approximately a 51% chance that at least 2 of them have the same birthday. With 50 people, the probability rises to 97%. With 70 people, it is almost certain that at least 1 pair shares a birthday. This result is called a paradox not because it is logically contradictory, but because it contradicts most people's intuitive expectations so dramatically. The resolution to the paradox lies in understanding the difference between asking whether someone shares your specific birthday versus asking whether any 2 people in a group share any birthday. If you walk into a room of 23 people and ask whether anyone has the same birthday as you, the probability is quite low, only about 6%. But if you ask whether any 2 people in the room, including those you are not personally comparing to, share a birthday, the probability is much higher because there are many possible pairs. With 23 people, there are 253 distinct pairs of people. Each pair has a 1 in 365 chance of sharing a birthday if we ignore leap years, and the probability that at least 1 pair matches accumulates quickly as the number of pairs increases. The calculation involves finding the probability that all pairs have different birthdays and subtracting from 1. This yields the counterintuitive result that matches become likely with surprisingly small groups. The birthday paradox illustrates a broader phenomenon where coincidences are much more common than intuition suggests. Rare events become probable when there are many opportunities for them to occur. Imagine playing the lottery. Your chance of winning on any single ticket is minuscule, but if millions of people play, it becomes likely that someone will win. Yet when someone does win, it feels like a remarkable coincidence, and people often seek explanations involving luck or fate. In reality, such outcomes are statistically expected given the number of trials. Similarly, many apparent coincidences in everyday life arise from the sheer number of opportunities for unusual events. You dream about an old friend, and they call you the next day, which seems like psychic connection or meaningful synchronicity. But you have dreams every night and know hundreds of people, creating thousands of opportunities per year for this kind of temporal coincidence. Some matches are inevitable, and the ones that occur stand out in memory, while the many non-matches are forgotten. The unsettling implication of the birthday paradox and related phenomena is that our intuitions about probability and coincidence are systematically miscalibrated.
We overestimate the significance of coincidences because we do not instinctively account for the number of opportunities for unusual events. This leads to various cognitive biases and superstitious beliefs. People see patterns in random data, attribute causal significance to chance correlations, and develop elaborate theories to explain coincidences that require no explanation beyond ordinary statistics. In medical contexts, patients may believe that a treatment worked because they improved after taking it, failing to consider that many illnesses improve on their own over time. The timing of treatment and improvement creates a coincidence that feels meaningful but may have no causal connection. In legal contexts, prosecutors sometimes present statistical evidence of rare matches, such as DNA profiles or forensic evidence, without properly accounting for the number of comparisons made, leading to incorrect assessments of guilt. Understanding probability deeply and intuitively is difficult, and our natural tendencies lead us astray in systematic ways. Recognizing these limitations is both intellectually unsettling and practically important for making rational decisions in an uncertain world.
The Sleeping Beauty problem is a philosophical puzzle in probability theory that has generated intense debate among experts because it highlights fundamental disagreements about how to interpret probability in situations involving self-locating information. The setup is as follows. Sleeping Beauty volunteers for an experiment. On Sunday, she is put to sleep. A fair coin is then flipped. If the coin lands heads, she is awakened on Monday, interviewed, and then the experiment ends. If the coin lands tails, she is awakened on Monday, interviewed, her memory of the Monday awakening is erased, she's put back to sleep, and then she is awakened again on Tuesday and interviewed again. Each time she is awakened, she knows the setup of the experiment but has no information about whether it is Monday or Tuesday or how the coin landed. The question is, when Sleeping Beauty is awakened and interviewed, what probability should she assign to the proposition that the coin landed heads? One answer, called the Haffer position, argues that the probability is 1/2. Before the coin was flipped, Sleeping Beauty would have assigned a 50% chance to heads and 50% to tails. The coin flip is objective random event, and being awakened does not change the physical probability of how the coin landed. Therefore, upon awakening, she should still believe the probability is 1/2 for heads. The other answer, called the thirder position, argues that the probability is 1/3. Here's the reasoning. There are 3 equally likely scenarios from Sleeping Beauty's perspective when she wakes up. Either the coin landed heads and today is Monday, or the coin landed tails and today is Monday, or the coin landed tails and today is Tuesday. She has no information to distinguish among these 3 scenarios, so she should assign equal probability to each. In 2 of the 3 scenarios, the coin landed tails, so the probability of tails is 2/3 and the probability of heads is 1/3. Both arguments seem compelling, yet they reach different conclusions. The Haffer and thirder positions represent different philosophies about what probability means. Haffer's emphasize the objective frequency interpretation of probability, where the coin has an inherent 50% chance of landing heads, and this objective fact is unchanged by Sleeping Beauty's subjective experience of being awakened. Thirders emphasize the subjective Bayesian interpretation of probability, where probability measures degree of belief and should be updated based on all available information, including self-locating information about which possible experience one is having. The disagreement is not about the facts of the scenario, which both sides agree on, but about the correct way to reason under uncertainty when multiple indistinguishable observations correspond to the same underlying event. This reveals that probability is not a simple objective property that can be read off from a situation, but rather depends on subtle choices about reference classes and conditioning. The Sleeping Beauty problem is unsettling because it shows that experts can disagree fundamentally about how to reason in probabilistic situations, even when all the facts are clear and all parties are using rigorous mathematical reasoning. There is no consensus resolution, and the debate continues in academic philosophy and decision theory. Some researchers argue that the disagreement is merely verbal, with both sides correct under different interpretations of what the probability question is asking. Others believe there is a fact of the matter about the correct probability, but disagree about the methodology that determines it. This lack of consensus about basic probability questions suggests that our understanding of uncertainty and rational belief is less solid than we might hope. If trained experts cannot agree on how to assign probabilities in a clearly defined scenario, what hope do ordinary people have of reasoning correctly about the far messier and more ambiguous uncertainties of real life? The problem serves as a reminder that probability theory, despite its mathematical precision, rests on conceptual foundations that remain philosophically contested. The universe may or may not operate according to probabilistic laws at a fundamental level, but even if it does, translating those laws into practical reasoning about belief and decision remains an unsolved challenge with unsettling implications for epistemology and rationality.
The Collatz conjecture is one of the simplest to state, yet most frustratingly difficult unsolved problems in mathematics. The rule is remarkably straightforward. Take any positive whole number. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. Repeat this process with the resulting number, applying the same rule over and over. The conjecture states that no matter what number you start with, you will eventually reach the number 1. Once you reach 1, the sequence enters a loop. 1 is odd, so it becomes 4, then 4 is even, so it becomes 2, then 2 becomes 1 again, cycling forever. The conjecture asserts that every starting number eventually falls into this cycle. Despite the simplicity of the rule, mathematicians have been unable to prove this conjecture since it was first proposed by Lothar Collatz in 1937. Computers have verified the conjecture for enormous starting numbers, far beyond trillions, and no counterexample has ever been found. Yet a general proof remains elusive, and it is possible that the conjecture is false and some starting number leads to a sequence that grows without bound or enters a different cycle that never reaches 1. What makes the Collatz conjecture particularly unsettling is the apparent randomness of the sequences it generates despite the deterministic rule. If you start with different numbers, the sequences behave unpredictably. Some numbers reach 1 very quickly. Starting with 16, you get 8, 4, 2, 1 in just 4 steps. Other numbers take much longer and reach surprisingly high values before eventually descending to 1. Starting with 27, the sequence climbs all the way up to 9,232 before gradually working its way back down, taking 111 steps to reach 1. There is no obvious pattern determining which numbers will produce long sequences or high peaks. The behavior seems chaotic, sensitive to the specific starting value in ways that are difficult to predict or characterize. This combination of simple rules and complex behavior is a hallmark of chaotic systems, which are deterministic yet effectively unpredictable due to their sensitivity to initial conditions. Many mathematicians have attempted to prove the Collatz conjecture using various techniques, but the problem has resisted all approaches so far. The difficulty stems from the mixture of multiplication and division in the rule, which prevents the application of standard number theoretic methods. Multiplication by 3 and adding 1 has a different algebraic structure than division by 2, and the interplay between these operations creates complexity that is hard to analyze. Some mathematicians believe the conjecture may be undecidable, meaning it can neither be proved nor disproved within the standard axioms of mathematics, similar to Gödel's incompleteness results.
If the conjecture is undecidable, then there would be no general proof of its truth or falsity, though it could still be true for all numbers in a sense that cannot be formally demonstrated. Other mathematicians believe a proof will eventually be found, perhaps requiring new mathematical tools or insights that have not yet been developed. The conjecture has inspired significant research into dynamical systems, number theory, and computational mathematics, even though the problem itself appears to have no practical applications. The philosophical unsettling aspect of the Collatz conjecture is what it suggests about the limits of mathematical knowledge and the nature of simplicity. A rule that any child can understand and apply generates behavior that the world's best mathematicians cannot fully explain or predict. This illustrates that complexity can emerge from simple foundations, and that our ability to formulate a question does not guarantee our ability to answer it. The conjecture also highlights the role of computation in modern mathematics. Before computers, mathematicians could only verify the conjecture for small numbers by hand. Computers have extended verification into the trillions and beyond, providing strong empirical evidence for the conjecture's truth. But empirical evidence, no matter how extensive, is not a proof. Mathematics demands certainty, and the gap between computational verification and logical proof represents a tension in contemporary mathematical practice. Some results are known to be true in the sense that no reasonable person doubts them, yet they remain technically unproven. The Collatz conjecture occupies this strange space, almost certainly true, but possibly forever beyond the reach of a proof, a simple question that may never receive a complete answer. Irrational numbers are numbers that cannot be expressed as a ratio of two integers. They have decimal expansions that go on forever without repeating any pattern. The discovery of irrational numbers was deeply troubling to ancient Greek mathematicians who believed that all quantities could be expressed as ratios of whole numbers. The Pythagoreans, followers of the mathematician Pythagoras, held that number and ratio were the fundamental principles underlying reality. According to legend, one of the Pythagoreans discovered that the square root of 2, which is the length of the diagonal of a square with sides of length 1, cannot be expressed as a fraction. This discovery was so disturbing to the Pythagorean worldview that it was supposedly kept secret, and some stories suggest the discoverer was killed to prevent the knowledge from spreading. Whether or not these dramatic stories are true, the existence of irrational numbers certainly represented a crisis in Greek mathematics, forcing a reconceptualization of the relationship between geometry and arithmetic. The proof that the square root of 2 is irrational is elegant and uses proof by contradiction. Assume the square root of 2 can be written as a fraction in lowest terms, meaning the numerator and denominator have no common factors. Let us call this fraction a over b. Squaring both sides, we get 2 equals a squared over b squared, which rearranges to 2b squared equals a squared. This means a squared is even. And if a squared is even, then a itself must be even because the square of an odd number is odd. Since a is even, we can write a as 2 times some integer. Let us call it c. Substituting this into our equation, we get 2b squared equals 4c squared, which simplifies to b squared equals 2c squared. This means b squared is even, so b must be even. But now we have shown that both a and b are even, which contradicts our assumption that the fraction was in lowest terms with no common factors. This contradiction means our initial assumption was false, and the square root of 2 cannot be expressed as a fraction. It is irrational. Once mathematicians accepted the existence of irrational numbers, they discovered that irrationals are far more common than rationals. In fact, in a precise mathematical sense, almost all real numbers are irrational. The rational numbers, despite being infinite in quantity, form a set of measures 0 on the real number line. If you were to choose a random real number, the probability of getting a rational number is exactly 0. This seems paradoxical because we primarily work with rational numbers in everyday life. Measurements, prices, quantities, all are expressed as fractions or terminating decimals, which are rationals. But the rationals are just a sparse scattering of points along the continuum of real numbers, with irrational numbers filling all the gaps in between. The real number line is dense with irrationals, packed so tightly that between any two rational numbers, no matter how close, there exist infinitely many irrational numbers. Conversely, between any two irrational numbers, there exist infinitely many rationals. The rationals and irrationals are interwoven in an infinitely intricate pattern, each dense in the real numbers, yet the irrationals overwhelmingly more numerous. The unsettling aspect of irrational numbers goes beyond their existence and prevalence. Many important mathematical constants are irrational, including the square root of 2, the golden ratio, pi, and e. These numbers appear throughout mathematics and nature, yet they cannot be expressed exactly using finite information. Pi, the ratio of a circle's circumference to its diameter, has a decimal expansion that goes on forever without repeating any pattern. Mathematicians have computed trillions of digits of pi, and the digits show no discernible pattern. They appear random despite being completely determined by the geometric definition of a circle. This raises deep questions about the relationship between geometry and arithmetic. A simple, perfect geometric form, yet the number that describes its fundamental proportions is infinitely complex when expressed in decimal notation. Is this complexity a fundamental feature of reality or an artifact of our choice to use base 10 representation? Even in other bases, pi remains irrational and non-repeating, suggesting the complexity is inherent rather than representational. The real number line is dense with irrationals, packed so tightly that between any two rational numbers, no matter how close, there exist infinitely many irrational numbers. Conversely, between any two irrational numbers, there exist infinitely many rationals. The rationals and irrationals are interwoven in an infinitely intricate pattern, each dense in the real numbers, yet the irrationals overwhelmingly more numerous. The St. Petersburg Paradox is a problem in probability theory and decision theory that challenges our understanding of rational behavior and expected value. The paradox involves a game with the following structure. A fair coin is flipped repeatedly until it lands heads. If heads appears on the first flip, you win $2 and the game ends. If heads appears on the second flip, you win $4. If heads appears on the third flip, you win $8. In general, if heads first appears on the nth flip, you win 2 to the power of n dollars. The question is, how much should you be willing to pay to play this game? The expected value of the game can be calculated by multiplying each possible payout by its probability and summing the results. The probability that heads appears on the first flip is 1/2, and the payout is $2, contributing $1 to the expected value. The probability that heads first appears on the second flip is 1/4, and the payout is $4, contributing another $1. Each subsequent outcome also contributes $1 to the expected value, and since there are infinitely many possible outcomes, the expected value is infinite. According to the principle of maximizing expected value, you should be willing to pay any finite amount of money to play this game, because the expected return is infinite. The paradox arises because no reasonable person would actually pay a large sum of money to play this game, even though the expected value is infinite. Most people would be unwilling to pay more than a few dollars, certainly not hundreds or thousands of dollars, despite the mathematical calculations suggesting an infinite expected value.
This disconnect between mathematical expectation and intuitive reasonableness reveals limitations in the expected value framework for decision-making. The problem is that the enormous payouts in the St. Petersburg game occur with such tiny probabilities that they are effectively irrelevant to real decisions. To win $1 million, heads must first appear on the 20th flip, which happens with probability less than 1 in a million. To win $1 billion requires the 40th flip, probability less than 1 in a trillion. These outcomes contribute to the infinite expected value calculation, but they are so unlikely that most people reasonably ignore them when deciding how much to pay. Various solutions have been proposed to resolve the St. Petersburg Paradox. One approach, suggested by Daniel Bernoulli in 1738, introduces the concept of utility, which measures subjective value rather than monetary value. Bernoulli proposed that people do not value money linearly. An extra dollar is worth more to someone with little money than to someone with great wealth. If utility increases logarithmically with money, then the expected utility of the St. Petersburg game is finite, even though the expected monetary value is infinite. This resolves the paradox by explaining why people rationally refuse to pay large amounts for the game. The extreme payouts have such low probability that their contribution to expected utility is negligible. Another approach considers realistic constraints, such as the fact that no casino could actually pay arbitrarily large amounts. If we cap the maximum payout at some reasonable value based on the casino's wealth, the expected value becomes finite and the paradox disappears. But this feels like avoiding the problem rather than solving it, because the original mathematical question concerns the idealized game without such limitations. The St. Petersburg Paradox is philosophically unsettling because it shows that expected value, despite being a cornerstone of probability theory and rational decision-making, does not always align with reasonable behavior. It suggests that human rationality is more nuanced than simple expected value maximization. We incorporate considerations of risk, likelihood, and diminishing marginal utility that are not captured by naive expected value calculations. The paradox also connects to broader questions about infinity and its role in practical reasoning. Infinite expected values arise in various scenarios, not just in contrived gambling games, and handling these cases requires care. In economics, some models of investment or innovation produce infinite expected returns under certain assumptions, yet people do not invest unlimited resources in such opportunities. Understanding why requires going beyond expected value to consider risk aversion, liquidity constraints, time preferences, and other factors that shape real human decisions. The gap between idealized mathematical rationality and actual human behavior remains an active area of research in behavioral economics and decision theory, with the St. Petersburg Paradox serving as a classic example of the puzzles that arise when we try to apply mathematical models to messy reality. Benford's law is a surprising statistical regularity, stating that in many naturally occurring collections of numbers, the first digit is not equally likely to be any digit from 1 to 9, but instead follows a specific distribution where small digits appear as the first digit much more frequently than large digits. Specifically, the probability that the first digit is 1 is about 30%, while the probability that the first digit is 9 is less than 5%. This is counterintuitive because if numbers were random, we would expect each non-zero digit to appear as the first digit with equal probability, about 11%. Yet Benford's law has been observed to hold for an astonishing variety of data sets, including population sizes of countries, lengths of rivers, financial data, physical constants, house prices, death rates, and many others. Not all datasets follow Benford's law, but those that span multiple orders of magnitude and arise from multiplicative or exponential processes tend to conform closely to the predicted distribution.
The law was first noticed by astronomer Simon Newcomb in 1881, who observed that the pages of logarithm tables corresponding to numbers starting with 1 were more worn than pages for numbers starting with 9, suggesting that scientists looked up numbers beginning with 1 more frequently. The observation was largely forgotten until physicist Frank Benford rediscovered it in 1938 and documented it across thousands of datasets, giving the law his name. But why does this pattern exist? The intuitive explanation involves scale invariance and the way measurements accumulate across different orders of magnitude. If a quantity can range over many powers of 10, and if there is no natural preferred scale, then the distribution of first digits should be invariant under changes of units. Benford's law is the unique distribution that satisfies this scale invariance property. When you convert measurements from meters to feet or from dollars to euros, Benford's law continues to hold, whereas a uniform distribution would not. A deeper mathematical explanation involves logarithms and the distribution of mantissas. If you take the logarithm base 10 of a number, the integer part tells you the order of magnitude, and the fractional part, called the mantissa, determines the first digit. For a number to start with the digit 1, its base 10 logarithm's mantissa must be between 0 and log of 2, which is approximately 0.301. For the first digit to be 9, the mantissa must be between log of 9 and 1, an interval of width approximately 0.046. If the mantissas are uniformly distributed between 0 and 1, which happens for many naturally occurring datasets, then the probability of each first digit matches Benford's law. The uniformity of mantissas arises naturally when datasets span many orders of magnitude without clustering at particular scales, which is why Benford's law applies broadly to diverse phenomena. Benford's law has practical applications in detecting fraud and irregularities in financial and scientific data. When people fabricate data or manipulate figures, they tend to use digits uniformly, not realizing that real-world data typically follows Benford's distribution. Forensic accountants use it to flag suspicious datasets for further investigation. Tax authorities have used it to identify fraudulent tax returns, and election monitors have used it to detect possible vote manipulation. However, the law must be applied carefully because not all datasets should follow Benford's law, and deviations do not always indicate fraud. Datasets that are constrained to a narrow range or that involve assigned numbers like telephone numbers or lottery numbers do not follow Benford's law. The unsettling aspect of Benford's law is that it reveals hidden structure in what appears to be random variation. Numbers drawn from reality are not as random as they seem. They carry signatures of the processes that generated them, and these signatures can be detected through statistical analysis. This has implications for privacy and security, suggesting that even anonymized numerical data may contain patterns that reveal information about their source or allow detection of manipulation. The universe is patterned in subtle ways, and careful observation can uncover regularities where we expected only chaos. The four-color theorem states that any map drawn on a plane can be colored using at most 4 colors, in such a way that no two adjacent regions share the same color. Two regions are considered adjacent if they share a boundary segment, not just a single point. This conjecture was proposed in 1852 and became one of the most famous unsolved problems in mathematics for over a century. The theorem seems plausible based on experimentation. Cartographers had long observed that 4 colors suffice for any map they encountered in practice, and no one could construct a map requiring 5 colors. Yet proving that 4 colors always suffice for every possible map, no matter how complex, turned out to be extraordinarily difficult. The problem is that there are infinitely many possible map configurations, and checking them one by one is impossible. Mathematicians needed a general argument that would cover all cases simultaneously. Many attempted proofs were published over the years, but they all contained errors or gaps. The problem resisted the standard techniques of mathematical proof, and some mathematicians began to suspect it might be undecidable or false. In 1976, Kenneth Appel and Wolfgang Haken finally proved the four-color theorem, but their proof was controversial because it relied heavily on computer calculations. They reduced the infinite variety of possible maps to a large but finite set of special cases, about 2,000 configurations, and then used a computer to verify that each case could be four-colored. The computer calculations took hundreds of hours, and the proof was far too long and complex for any human to check completely by hand. This was the first major mathematical theorem proved with essential computer assistance, raising philosophical questions about the nature of proof and mathematical knowledge. Traditionally, mathematical proofs are arguments that can be verified by human mathematicians through careful reasoning. A proof should provide insight into why the theorem is true, not just confirm that it is true. The Appel-Haken proof of the four-color theorem provides confirmation but limited insight. We know the theorem is true because the computer checked all the necessary cases, but we do not have a deep understanding of why four colors suffice or what underlying principle makes four the magic number. Some mathematicians found this unsatisfying and continued searching for a more elegant conceptual proof that would provide understanding. In the decades since 1976, the proof has been simplified and improved, and the number of special cases has been reduced, but all known proofs still require computer verification of a large case analysis. The theorem has been independently verified by multiple teams using different methods, increasing confidence in its correctness, but the reliance on computation remains. The four-color theorem is unsettling for several reasons. First, it shows that some mathematical truths may be inherently computational, requiring checking many cases without a unifying conceptual framework. This challenges the classical ideal of mathematics as a realm of pure reason, where insight and elegance are paramount. Second, it raises questions about certainty in mathematics. Computer programs can contain bugs, and hardware can malfunction. Although the four-color theorem has been verified multiple times with different programs and approaches, reducing the likelihood of error, we still depend on the correctness of complex software and hardware systems. This is a different kind of confidence than the absolute certainty we feel when following a traditional human-readable proof. Third, the theorem highlights a gap between mathematical existence and human understanding. We know four colors suffice, but we may never achieve the kind of intuitive understanding that mathematicians traditionally seek. Some truths about abstract structures may be too complex for human minds to grasp fully, accessible only through delegation to computational methods. This is both humbling and unsettling, suggesting limits to human cognition that we must work around through technological augmentation. Prime numbers that differ by 2, such as 3 and 5, 11 and 13, or 17 and 19, are called twin primes. These pairs of primes separated by the minimal possible gap have fascinated mathematicians for centuries. The twin prime conjecture asserts that there are infinitely many twin prime pairs, that no matter how far you travel along the number line, another pair of twin primes awaits discovery somewhere ahead. This conjecture is ancient, possibly known to the Greeks, and remains unproven despite enormous effort by mathematicians over millennia. The difficulty arises because while we know many properties of primes collectively, predicting the behavior of individual primes or specific patterns within primes is extremely hard. Twin primes seem to become increasingly rare as numbers grow larger, but whether they eventually cease entirely or continue infinitely is unknown. In 2013, mathematician Yitong Zhang made a stunning breakthrough by proving a weaker result that energized the field. Zhang proved that there are infinitely many pairs of primes separated by at most 70 million. This was the first proof that prime gaps are bounded infinitely often, a major step toward proving the twin prime conjecture. Although 70 million is far from 2, the achievement was revolutionary because it showed that bounded gaps between primes occur infinitely often, whereas previously mathematicians could not even prove this for any finite bound. Following Zhang's work, a collaborative project called Polymath used crowdsourced mathematical effort to reduce the bound from 70 million down to 246 using existing methods. If the bound could be reduced all the way to 2, the twin prime conjecture would be proved. But progress has stalled, and closing that final gap from 246 to 2 appears to require fundamentally new ideas or techniques. The twin prime conjecture is part of a broader landscape of conjectures about prime gaps and prime patterns. The broader Hardy-Littlewood conjectures proposed in the early 20th century make predictions about the distribution of prime constellations, specific patterns of primes separated by fixed gaps. These conjectures include the twin prime conjecture as a special case and extend to more complex patterns involving 3 or more primes. If the Hardy-Littlewood conjectures are true, then primes exhibit a remarkable regularity in their distribution, despite their apparent randomness. They predict not just that twin primes are infinite, but give asymptotic formulas for approximately how many twin primes exist below a given bound, formulas that match numerical data remarkably well. Yet proving these conjectures has proven extraordinarily difficult, suggesting that our current mathematical techniques are insufficient for fully understanding prime distributions. The unsettling nature of the twin prime conjecture lies in the combination of simplicity, importance, and intractability. The statement is easy to understand and concerns one of the most fundamental objects in mathematics, prime numbers. Yet we cannot prove or disprove it despite centuries of effort by brilliant minds. This suggests that mathematics contains truths that lie just beyond our current reach, perhaps requiring insight or methods that have not yet been imagined. The conjecture also connects to deep questions about determinism and pattern. Prime numbers are completely deterministic, defined by a simple rule, yet their distribution feels random, and extracting patterns from this pseudo-randomness is profoundly difficult. If we cannot fully understand something as basic as the gaps between primes, what hope do we have of understanding more complex structures? Yet the partial progress, such as Zhang's theorem, provides hope that patient effort and clever ideas can push the boundaries of knowledge incrementally. The twin prime conjecture stands as a monument to both the power and the limits of human mathematical understanding, a simple question that may someday be answered or may remain forever just out of reach. For over 2,000 years, Euclidean geometry was considered the absolute truth about the structure of space. Euclid's axioms and theorems described the properties of points, lines, and shapes in a framework that seemed self-evidently correct and unchangeable. One of Euclid's axioms, the parallel postulate, states that given a line and a point not on the line, there is exactly one line through the point that never intersects the original line. This axiom is less intuitive than Euclid's other axioms, and mathematicians for centuries attempted to prove it from the other axioms, believing it should be a theorem rather than an assumption. All attempts failed, and in the early 19th century, mathematicians began exploring what happens if the parallel postulate is replaced with alternatives. This led to the discovery of non-Euclidean geometries, revolutionary systems where the rules of geometry are fundamentally different from Euclid's. In hyperbolic geometry, also called Lobachevskian geometry, the parallel postulate is replaced with the assumption that through a point not on a line, there are infinitely many lines that never intersect the original line. This creates a geometry where the angles of a triangle sum to less than 180 degrees, and the circumference of a circle grows exponentially with its radius. The space has constant negative curvature, like a saddle shape. In elliptic geometry, also called Riemannian geometry, there are no parallel lines at all. Every pair of lines intersects, and triangles have angle sums greater than 180 degrees. The space has constant positive curvature, like the surface of a sphere. Both of these geometries are internally consistent, meaning they contain no logical contradictions, and they are just as mathematically valid as Euclidean geometry. This was a shocking discovery because it meant that the structure of space is not dictated by pure logic, but rather depends on which axioms we choose to assume. The existence of non-Euclidean geometries had profound philosophical implications. It showed that mathematical truth is not absolute, but relative to foundational assumptions. Different geometries describe different possible spaces, and the question of which geometry describes the actual physical space we inhabit is an empirical question, not a purely logical one. For a long time, it seemed that physical space must be Euclidean because that matched our everyday experience. But in the early 20th century, Einstein's general theory of relativity revealed that the universe is actually described by a non-Euclidean geometry where space-time is curved by mass and energy. The geometry of spacetime near a massive object like the Sun is not Euclidean, and this curvature explains gravitational effects. Light travels along geodesics, the straightest possible paths in curved spacetime, and these paths bend near massive objects, a prediction confirmed by astronomical observations during a solar eclipse in 1919. The universe itself is a non-Euclidean structure, validating the abstract mathematical exploration that had seemed like mere curiosity a century earlier. The unsettling aspect of non-Euclidean geometry is the realization that our intuitive understanding of space, built from everyday experience, is only an approximation valid in limited contexts. The flat Euclidean space we perceive is an approximation that works well at human scales and low speeds, but it breaks down at cosmic scales and extreme conditions. The true geometry of the universe is curved and dynamic, changing in response to the distribution of matter and energy. This challenges our sense of objective reality and stable truth. The rules of geometry, which seemed as certain as anything could be, turn out to be contingent on the physical state of the universe. Furthermore, the discovery of non-Euclidean geometries opened the door to even more exotic mathematical spaces with strange properties, including higher dimensional spaces, spaces with variable curvature, and spaces with topological peculiarities like wormholes or closed time-like curves. Mathematics reveals that reality could have been structured in radically different ways, and understanding which mathematical structure describes our universe requires observation and experiment, not just logical deduction. The firmest ground we thought we stood on, the geometry of space itself, turned out to be more flexible and mysterious than anyone had imagined. Human perception is limited to 3 spatial dimensions: length, width, and height, and we struggle to visualize anything beyond this. Yet mathematics allows us to define and study spaces with any number of dimensions, and these higher dimensional spaces turn out to be essential for understanding physics, data analysis, and many other fields. A 4-dimensional space is defined mathematically by requiring 4 coordinates to specify a point, just as 3-dimensional space requires 3 coordinates. We can reason about 4-dimensional geometry using algebraic methods, even though we cannot visualize it directly. For example, a 4-dimensional hypercube, called a tesseract, is the 4-dimensional analog of a cube, with 16 vertices and 24 square faces. Although we cannot picture the tesseract in its full 4-dimensional glory, we can study its properties mathematically and even create 3-dimensional projections or cross-sections that give us glimpses of its structure. Higher dimensional spaces have counterintuitive properties that violate 3-dimensional intuition. In higher dimensions, spheres behave strangely. In 3 dimensions, most of a sphere's volume is concentrated near the surface, with the very center being a single point. But in higher dimensions, the situation becomes extreme. In very high dimensions, almost all of a sphere's volume is concentrated in a thin shell near the surface, and the interior is nearly empty by comparison. Stranger still, in high dimensions, the volume of a sphere of radius 1 is much smaller than the volume of the enclosing cube. As dimensions increase, the sphere shrinks relative to the cube because most of the cube's volume is in the corners, far from the center, and these corners lie outside the sphere. In infinite dimensions, the sphere has effectively 0 volume compared to the cube, a result that seems absurd but follows rigorously from the mathematics. Physics makes extensive use of higher dimensional spaces. Einstein's spacetime is a 4-dimensional continuum with 3 spatial dimensions and 1 time dimension, unified into a single geometric structure. String theory, a candidate for unifying quantum mechanics and general relativity, proposes that the universe has 10 or 11 dimensions, with the extra dimensions beyond the familiar 4 being compactified or curled up at scales too small to detect. These extra dimensions would be real physical dimensions, not just mathematical abstractions, but they are hidden from direct observation. The geometry of these extra dimensions determines the physical laws we observe at macroscopic scales, so understanding their structure is crucial for understanding fundamental physics. This suggests that our familiar 3-dimensional space is only a small part of a much larger reality, and the true structure of the universe is vastly more complex than our senses reveal. The unsettling aspect of higher dimensions is the realization that our perceptual apparatus captures only a limited slice of reality, and the true nature of existence may lie in structures we cannot directly perceive or imagine. We are like 2-dimensional beings living on a flat surface, unaware of the 3rd dimension that extends above and below their plane. Just as such beings would struggle to understand 3-dimensional objects passing through their plane, appearing and disappearing mysteriously, we may be unable to fully comprehend aspects of reality that involve dimensions beyond our perceptual reach. Mathematics gives us tools to reason about these dimensions, but mathematical understanding is not the same as intuitive visualization. We can manipulate equations and derive results about higher dimensional spaces, but we cannot picture them in the mind's eye. This suggests a fundamental limitation of human cognition, where our thinking is constrained by the dimensionality of the space in which we evolved. Perhaps there exist intelligent beings in the universe with different perceptual systems who experience dimensions we cannot, and who would find our limitations as baffling as they find theirs. The concept of dimensions beyond 3 forces us to confront the possibility that the universe is far richer and stranger than our sensory experience suggests, and much of reality remains forever beyond our direct apprehension. Time seems to flow in one direction, from past to future, and this directional flow is deeply embedded in our experience and language. We remember the past, but not the future. We see effects following causes, and we observe systems evolving from order to disorder. Yet the fundamental laws of physics at the microscopic level are time-symmetric, meaning they work equally well whether time runs forward or backward. If you filmed a video of billiard balls colliding and played it in reverse, the reversed motion would still obey Newton's laws of motion. The equations of classical mechanics, electromagnetism, quantum mechanics, and even general relativity are symmetric under time reversal. This creates a deep puzzle. If the underlying laws do not distinguish past from future, why does the universe exhibit such a strong arrow of time? Why do we experience time as flowing in one direction? The answer involves entropy, a concept from thermodynamics that measures the disorder or randomness of a system. The second law of thermodynamics states that the total entropy of an isolated system never decreases over time. Entropy tends to increase, meaning systems evolve toward more disordered states. A hot cup of coffee cools down, spreading its heat energy to the surrounding air, increasing the overall entropy. Ice melts, gases mix, and structures decay. The direction of increasing entropy defines a thermodynamic arrow of time that aligns with our psychological arrow of time, the direction in which we perceive time flowing. But why does entropy increase? The statistical mechanics explanation is that high-entropy states are vastly more numerous than low-entropy states. There are many more ways for a system to be disordered than ordered, so if the system explores its possible states randomly, it is overwhelmingly likely to move toward higher entropy simply because there are more high-entropy states to move into. This makes the second law a probabilistic rather than absolute statement. Entropy increases because it is statistically favored, not because any fundamental law forbids entropy decrease. The puzzle deepens when we consider the early universe. The Big Bang was an extremely low entropy state, highly ordered and far from equilibrium. As the universe expands and evolves, entropy increases, driving the arrow of time we observe. But why did the universe begin in such a special low entropy state? This is one of the deepest unsolved questions in cosmology. If the initial state were random, we would expect high entropy from the start, and there would be no arrow of time, no evolution from order to disorder. The fact that our universe has a strong time asymmetry suggests that the initial conditions were highly atypical, requiring explanation. Some physicists propose that the low entropy beginning is an anthropic selection effect. Only universes with low initial entropy can support complex structures like galaxies, stars, and life, so we necessarily find ourselves in a universe with a time arrow. But this explanation feels unsatisfying because it does not explain why any universe would have low initial entropy. Other physicists speculate about mechanisms in quantum cosmology or theories of eternal inflation that might generate low entropy regions naturally within a larger multiverse, but these ideas remain speculative. The concept of entropy and the arrow of time are unsettling because they reveal a fundamental asymmetry in nature that seems to lack a deep explanation. Time's arrow emerges from statistical properties of large systems, not from the fundamental laws themselves. This suggests that the direction of time is not a basic feature of reality, but rather an emergent phenomenon arising from initial conditions and probability. Furthermore, entropy's increase is only a statistical tendency, not an absolute law. It is theoretically possible, though fantastically unlikely, for entropy to spontaneously decrease, for a shattered glass to reassemble itself, or for heat to flow from cold to hot. These events violate our expectations, but not any fundamental physical law. They are simply so improbable that they never occur in practice. The arrow of time, which feels so real and undeniable in our experience, is ultimately grounded in probability and cosmic history rather than logical necessity. This lends a contingent, almost fragile quality to one of the most basic aspects of existence, suggesting that in other universes with different initial conditions, time might not flow at all, or might flow in multiple directions, creating realities utterly alien to our experience. The continuum hypothesis, proposed by George Cantor in the late 19th century, concerns the possible sizes of infinite sets. Cantor proved that the set of natural numbers, which is countably infinite, is strictly smaller than the set of real numbers, which is uncountably infinite. He called the size of the natural numbers Aleph No, and the size of the real numbers the cardinality of the continuum. The continuum hypothesis asks whether there exists an infinite set with cardinality strictly between Aleph No and the continuum. Cantor believed no such intermediate infinity exists, meaning the continuum is the next larger infinity immediately after the countable infinity, but he could not prove it. The hypothesis became one of the most important unsolved problems in mathematics, listed as the first of Hilbert's 23 problems in 1900, a famous list of challenges for 20th century mathematics. In 1963, Paul Cohen proved a result that shocked the mathematical world. Using a technique called forcing, Cohen showed that the continuum hypothesis is independent of the standard axioms of set theory, known as ZFC. This means the hypothesis can neither be proved nor disproved from the usual foundations of mathematics. It is consistent to assume the hypothesis is true, and it is equally consistent to assume it is false. Mathematicians can choose to work in a mathematical universe where the hypothesis holds, or in one where it fails, and both choices lead to consistent systems with different properties. This independence result implies that the size of the continuum is not determined by the logical structure of mathematics alone, but requires an additional axiom or assumption beyond the standard framework. This was disturbing to many mathematicians because it suggested that set theory, the foundation of mathematics, contains fundamental ambiguities that cannot be resolved through logical deduction. Cohen's result raised deep questions about the nature of mathematical truth. If the continuum hypothesis can neither be proved nor disproved, is there still a fact of the matter about whether it is true? Some mathematicians, called Platonists, believe mathematical objects exist independently of human minds, and there is an objective truth about the size of the continuum even if we cannot prove it from our current axioms. According to this view, our axioms may simply be incomplete, failing to capture all truths about the mathematical universe, and we might someday discover new axioms that resolve the question. Other mathematicians, called formalists or constructivists, view mathematics as a human-created system of rules and definitions, and the independence of the continuum hypothesis shows us that we have freedom to choose different axiomatic frameworks leading to different mathematical universes. According to this view, asking whether the hypothesis is really true is meaningless because truth is relative to the axioms we adopt. The unsettling aspect of the continuum hypothesis independence is the implication that mathematics is not a single unified structure, but rather a landscape of possible systems, each consistent and valid within its own framework. This pluralism challenges the classical vision of mathematics as the discovery of eternal truths and replaces it with a more flexible view where mathematicians explore different possible worlds. It also highlights the role of choice and aesthetics in mathematics. If multiple axiom systems are consistent, how do we choose among them? Mathematicians may prefer axioms that lead to elegant theorems that align with intuitions about infinite sets, or that have applications in other areas of mathematics. But these are pragmatic or aesthetic criteria, not logical necessities. The continuum hypothesis remains unresolved not because it is too difficult, but because it lies outside the scope of logical proof within our current foundational framework. This suggests that the dream of reducing all mathematical truth to mechanical derivation from axioms, a dream pursued by formalists in the early 20th century, is fundamentally unattainable. Mathematics will always involve choices, interpretations, and philosophical commitments that go beyond pure logic, and the infinite richness of mathematical possibility ensures that exploration will never be exhausted.